Okay, here we have section 5.6, and we're going to look at some of these theorems and properties and all that. I'm not sure how many we'll get to in this first video, but we'll start with theorem 5.61, and they say if arg z1 equals theta 1 and arg z2 equals theta 2, then arg z1 times z2 is equal to theta 1 plus theta 2. Now, for them, you know, when they go through it, you have to go through this whole whole business of trig identities and stuff like that often, and that's where I went ahead and did e to the I theta thing. So what we could do is, we can just write, well, z1 equals some r e to the I theta 1, some r1, and z2 is equal to r2 e to the I theta 2. And so for this proof, now I just multiply z1, z2. Well, that's r1 e to the I theta 1, r2 e to the I theta 2, but that's just r1 times r2 e to the I theta 1 plus I theta 2. And then that's r1 r2 e to the I theta 1 plus theta 2. So there you go. We just get that proof right there, because now the arg of z1 times z2 is right there, theta 1 plus theta 2. And it's that simple using this exponential form here. Okay, so that's why I introduced it first. Okay. And let's see. Next they have corollary. Okay, so corollary 5.6.1, and you know, if we have arg z1 equals theta 1, arg z2 equals theta 2, dot, you know, arg zn equals theta n, then just by repeating over and over again, you know, you could use induction, you know, something like that, then we have that the arg of z1, z2 times zn is theta 1 plus theta 2 up to theta n. So yeah, that makes sense. And then they toss in another corollary that comes from this corollary, corollary 5.6.2, and that's simply, you know, if arg z equals theta, then arg z to the n is equal to n theta. And now actually, and that just, you know, comes from the previous corollary, make all those thetas the same, and you have n thetas. But another proof again, it can come straight from that exponential form, is that, if I let z equal r e to the I theta, then z to the n is equal to r e to the I theta to the n. But that's just r to the n e to the I n theta, using my properties of exponents. And so there you go. There's the argument, n times theta. So again, that form with the exponential is a really nice form. Then they have theorem 5.6.2, and they just do the multiplicative inverse. And so if arg z equals theta, then arg of the multiplicative inverse of z is equal to negative theta. But again, proof is very straightforward. I think it's definitely more straightforward than what they have, even, because if I just say z equals r e to the I theta, then z to the negative 1 is r e to the I theta to the negative 1, which is equal to r to the negative 1 e to the minus I theta. And so there again, there's the argument, minus I theta, but we're also seeing that then the modulus is, if we take the absolute value, then I know it's the modulus, because r might be a negative number. It could be. Typically, if I'm going to use this notation, r is a positive number, but it wouldn't have to be. And so we just take 1 over r there. Okay, so that was theorem 5.62, and that leads to a subtraction theorem, or actually corollary, 5.6.3. And so now if arg z1 is equal to theta 1 and arg z2 equals theta 2, then if we want arg z1 over z2, well, then that's just theta 1 minus theta 2. And of course you can get that, just from using, the previous corollary and doing something like, if I want arg z1 over z2, well, I could write that as the arg of z1 times z2 to the negative 1. And then use my addition theorem and my inverse theorem here, or corollaries, and get it that way. Okay, so I can, if I want, I can do it that way. That'll get it there, get me an answer pretty quickly. So so I have that, and so then that is theta 1 plus a negative theta 2, and so that's theta 1 minus theta 2. So there we go. Okay, so that's corollary 5.63, and then they have all these principal arguments, properties. So here are some things for principal arguments. And to tell you the truth, I don't really know how important they are. Just in that they have one, if you have arg z1, z2, then that's the principal argument of z1 plus the principal argument of z2, but then we might need something to fix it up, so they've got a k1 pi, 2 times k1 pi. And, just as an example of this, we can take two things like suppose I let z1 equal something like 1 let's see, 1 minus I. Okay, if I do something like that, and then probably even z2 equal negative 1 minus I. Okay, so when we look at those, if we were to multiply those, our principal argument of the answer doesn't just add. We're going to have to fudge it a little bit with this 2k pi up there. So let's see that. Now actually I'm just going to draw these. So 1 minus I, so there's 1, there's minus I, all right, that's out here. So if I want to, I can very quickly see that that's z1 equals the square root of 2 e to the I, what is that, 7 pi over 4, or well, if we go with principal argument, sorry, that's negative pi over 4. Okay, so I went with the principal argument, negative pi over 4, and similarly here, if I do that, for minus 1 and minus pi, that one's going to be z2 is equal to the square root of 2 e to the negative 3 pi over 4. Now, when I multiply these two, z1, z2, I get 2, because square root of 2 times square root of 2, and then e to the negative I pi. Okay, but here's the thing, the principal argument cannot be negative pi. Remember that if you want to go arg of some z, that's always between minus pi, but not inclusive, and less than or equal to pi. And so what you see is that this is a perfectly good representation for z1 times z2, but if I want the principal argument of z1, z2, that's going to equal pi, not minus pi. Okay, so what we did was we took minus pi, okay, the answer we got from adding those two principal arguments, and we added 2 pi to it. So our k1 in this case was 1. And now it could have been 0 because it could have all worked, but it didn't, so we had to do that. And so our principal argument is pi, not minus pi. Okay, and then they have other similar properties or equations they give. You know, and every single one of them are the theorems we've just done. They just need to possibly fudge that principal argument. If we want the principal argument here, it may not come directly from adding the principal arguments of the complex numbers we have. We may have to adjust it to get within between minus pi and pi. And so that's what I did here. Okay, and I think those are the theorems we do, because at that point it gets us to that definition of e to the I theta, and so we'll stop this video here.